And another important thing is these are the 5 important stages where most of the research people are estimating the environmental impact categories in life cycle assessment of concrete. First one is, as I said previously, global warming potential, GWP. Second one is energy consumption, which will be represented in terms of EE, embodied energy. Then water consumption, what are water usages. Then resource depletions and human exotoxicity. For better understanding, I will be moving towards a problem. We know that 1 ton of cement production will lead to 0.8 tons of carbon emission, but we don't know how. So I have worked out some problem related to that. It will be quite helpful for you for getting better idea. Just a second, there is an issue. System. Okay. GHGE is nothing but greenhouse gas emission during the production of raw material. In this slide, I will be just presenting carbon emission assessment of cement alone. So the amount of carbon emitted during the excavation of 1 ton of raw material, says for example limestone or clay, shown in this slide. So for drilling, blasting and loading of 1 ton of limestone, nearly 7 to 10 liters of fossil fuel is required. These data are taken from ACA as well as RILAM reports. So GHG emission, DNP represents drilling and blasting. So 7 liters of fossil fuels into 2.68 is nothing but the CO2 emission factor. So for drilling, blasting as well as loading of 1 ton of material, we require 18.76 kgs of CO2 is emitted. And next, loading. For loading the excavated materials to the transit truck, the amount of CO2 emission was found to be, for loading we require minimum of 3 liters of fossil fuel. So 3 into 2.68 will approximately give 8 kg of CO2 emission per ton. Okay. Generally, cement plants will be located nearby the limestone reservoirs to avoid the transportation costs. So in this case, I have taken a transport distance of 25 kilometers. So generally, if it increases the transportation, automatically the cost of manufacturing is also going to increase, as well as the amount of carbon emission is also going to increase. So the average heavy-duty truck has a fossil fuel efficiency of 2.5 kilometers per liter, and the truck has the loading capacity of nearly 25 metric tons. So in that cases, so for round trips, so 2 and 4, 25 plus 25, 50 kilometers. So 50 kilometers divided by 25, 2.5 will give you 20 liters. So for loading and unloading, you require 20 liters of fossil fuel into the carbon emission factor 2.68 will give you 53 kgs. So for transportation alone, for 25 metric tons of materials, we are going to emit 53.6 kgs of CO2. And in the case of 1 ton, 53.6 divided by 25, we can see that for 1 ton it is 2.14 kg. And next is GHG emission, that is greenhouse gas emission during calcination as well as coal burning process in the cement manufacturing unit. In that cases, in calcination process, you can able to see that 550 kgs of CO2 is being liberated for 1 ton, and 300 kgs of CO2 is being liberated for 1 ton. This data is also taken from the reports, RILAM reports. So I have not gone deeply into this calcination and coal burning process. If I go, then it is it will take some 1 or 2 hour time. So I have shortcut it over here. So total GHG emission in the cement plant alone will be 878.89 kgs per ton. So finally, after production producing the cement, it has to be transported to the market. So says for example, 100 kilometers it is away from the city. So up and down is 200 kilometers. So for round trip. So fuel consumption to again 200 divided by 2 point, you can able to get 80 liters. So into the carbon emission factor, you'll be getting 214 kgs of CO2. So for 25 tons, it can be estimated as 8.57 kgs. So moreover, totally, we can able to see that 887.5 kg CO2 is being emitted. So in this table, I have given different activities as well as amount of carbon emission being seen. So first drilling and blasting, 18.76 kgs of CO2 per ton. For loading, 8 kg CO2 per ton. For up and down transportation, 2.14 kg CO2 per ton. Then for calcination, it is defined 550. And for coal burning, it is defined 300. And fuel consumption again to the market from the cement manufacturing plant, it leads to 8.57. So totally 887.47 kgs of CO2 is being liberated for 1 ton of cement. So this is the reason why many people are quoting that therefore 1 ton of cement production leads to 0.8 and approximately 1 ton of carbon dioxide emission to the open environment. So similarly, I have worked it out for the energy requirement also. So 1 liter of diesel, says for example, has the energy of 0.0401 gigajoules of energy. So again, energy embodied energy, drilling and blasting 7 liters into emission factor, which will give you 0.28 gigajoules, and embodied energy in terms of loading, you will be getting 0.12 gigajoules. Then embodied energy in terms of raw material movements, you will be having 0.802 gigajoules, considering the up and down truck movement for 50 kilometers. Then embodied energy during clinker production. So that alone will be taking place of 3.4 gigajoules per ton. So for the developed clinker consumes 0.1 gigajoules for converting from clinker state to cement state. And then again EE for up and down cycle for the transportation, 0.128 gigajoules per ton. So total embodied energy was seen to be 4.83 gigajoules per ton from the raw material excavation, that is extraction, to the final delivery of the product to the market. So far we have seen about concrete and cement. Now we are moving towards water. So interesting facts about water is concrete is the second most consumable product in the world, and next water is the first consumable, highest consumable material in the world. So according to Niti Aayog report in 2018, 600 million people, that is approximately 60 crore people, are experiencing high extreme water stresses. And in the year 2019, the same Niti Aayog team has presented a report stating that 70% of the fresh water in India alone is being contaminated. So in this picture, I have shown water curing in the left top and water scarcity in the right bottom. So you can see that a person is spraying water for curing of column elements. So generally the people have used the wet gunny bags for wrapping along the column surface, and finally they will be pouring the water. Similar scenario is seen in this picture. So 1 billion cubic meters of concrete is being utilized for mixing and curing of concrete elements globally. So 1 billion cubic meter is nothing but 35.31 TMC. TMC is nothing but 1000 million cubic feet of water. So you just see 1 million cubic meter is equal to 35.31 TMC of water. So for real world example, for a better capture, I'll be stating that Mullai Periyar Dam has a total capacity of 15 TMC. 15 TMC. Only the Mullai Periyar Dam has the capacity of 15 TMC. It can't able to store beyond that. So you see that how much amount of water is being wasted, I mean used for concreting, casting as well as curing purpose in the concrete structures. So 15 is lower, 35.31 is much higher. So with this 35.31 TMC of water, we can able to feed 2 crore people. So for a particular year alone, so 130, if you supply 135 LPCD liters per capita per day, so 2 crore people will be benefited from this 35.31 liters of TMC of water. So in this slide, I have represented what are all the major consumers of water. First comes the agriculture. We all know that agriculture is the backbone of India. So it consumes 70% of the fresh water. And second is construction sector. Construction sector consumes 15% of the fresh water, and other industries 5%, and domestic use 10%. You see that domestic is only 10%. We are utilizing more than the domestic usage. So this data is also taken from World Green Building Council, the World Green Building Council, that is World GBC. Then why fresh water is being utilized for construction and why not others? So I have listed few things. First is chemical purity. Why? Because fresh water will not have any types of impure materials. That is one important thing. Another thing is cement hydration. Cement hydration is completely dependent upon the type of water you are using. If you are using fresh water, then obviously there will be a good strength gain. If not, then automatically it is going to affect your strength of the concrete. Why? Because in the case of reinforced concrete structure, you will be using steel grades, steel reinforcements of grade 415 or 500 or 250 or whatever it may be. So if you are using any impure water, automatically this enters into the concrete pore and it tends to affect the concrete reinforcement, and it finally leads to degradation of the entire structure, leads to global failure. Not the local failure, it leads to global failure. And another one is chlorides. Chlorides are generally an important enemy for the concrete. Why? Because most of the areas in Coimbatore as well as in southern part of Tamil Nadu, we can able to see that most of the waters are rich in chlorides. So if we use that type of water, then automatically the structure will corrode and it leads to degradation. And another important thing is structural integrity. Next is aesthetic and surface issues. If you're using salty water, generally there will be corrosion. If you're using high lime water, then automatically the surface will tends to look like white deposits. Says, for example, reference will be seen in all the surfaces of the concrete, and it will leads to dampness and finally leads to corrosion, spalling, and so on things. This is the main reasons why people are using fresh waters rather than going for a recycled or treated water for curing of concrete elements.